Okay, so let us start with the concept review. First, we would like to know how to understand the limit of a certain function. And yeah, we start with the following function. Suppose that we are given f of x equals to x minus 3 divided by x squared minus 9. And note that this function is undefined at 3 because its denominator will becomes 0 if I substitute x equals to 3. But the limit exists at 3. To be precise, if I calculate its limit, then, okay, so f of x, I will use the 1a, f of x equals to x minus 3 divided by x squared minus 9. Okay. And then we want to know what is the limit of x tends to 3 of f of x. Okay. Okay, so the idea is that here x is undefined at 3, but I want to know the value of its limit. So here, limit x tends to 3 of x minus 3 divided by x squared minus 9. And here, we know that x is not 3. So actually, I can divide x squared minus 9 there by x minus 3. And to be precise, I will write it as limit x tends to 3 of here, where is this? X minus 3 divided by x minus 3 multiplied by x plus 3. So in the end, since x tends to 3 means x minus 3 is non-zero. So x minus 3 divided by x minus 3 is 1. So finally, I will have limit x tends to 3 of 1 over x plus 3. And in this case, I will have its limit by the limit theorem, or we know that when x is approaching 3, then x plus 3 is approaching 6. So in the end, I have 1 over 6. Okay. So it's quite simple here. And yeah, this is the difference between the value of f at 3 and the limit of f at 3. Okay. The value of f at 3 is undefined, but its limit is 1 over 6. Okay. Okay. Any question so far at this point? Okay. Let us continue. So the next one, okay, we have the left hand limit and the right hand limit. So the right hand limit of f at 1 is 1, and the right hand is limit is 1. The left hand limit is 2. So here we have the case when the left hand limit is not equal to the right hand limit. Okay, so the conclusion is that the function does not have a limit, or the limit of f at x equals to 1 does not exist. Okay. Where is the whiteboard then? So here, b, the limit x tends to 1, f of x equals to 1, and the limit x tends to 1 from the left of f of x equals to 2. Here we have the limit x tends to 1 minus of fx is not equal to limit x tends to 1 plus f of x. So the left hand limit is not equal to the right hand limit. So the conclusion is the limit x tends to 1 of f of x here does not exist. Okay, the limit does not exist. Okay, so that's how we check the existence of the limit, namely we compare the value of left hand limit and the right hand limit. If both are the same, then the limit exists and also equals to that value. And if the left hand limit is not equal to the right hand limit, then the limit does not exist. Okay, any question or comment so far up to this point? Is it clear? Okay, so let us continue. Now, let us move to 1C. Here I have, okay, the following one. If, okay, so this is a kind of exercise in considering the epsilon delta definition of the limit. So if absolute value of x minus 1 is less than something, then we have the conclusion 5x minus 5 is less than epsilon. Okay, so in this case, if I consider the answer, so if absolute value of x minus 1 is less than blah blah blah, then absolute value of 5x minus 5 is less than epsilon. So the answer will depend on the value of epsilon then. Okay, how do we prove this? How do we obtain this? This is unknown quantity. Here I will write 5x minus 5 to be absolute value of 5 multiplied by x minus 1. Okay, and then of course I can write this as 5 multiplied by absolute value of x minus 1. Okay, okay, now I will have this unknown variable, and then I want to have this is 5 epsilon. This one become epsilon. Okay, so let us write this as a delta. Okay, write this as a delta. Then I should have 5 delta, and then I want to have 5 delta equals to epsilon here. Okay, so in order to have epsilon, then the choice of delta will be epsilon over 5. Okay, it's of this value. So the answer will be epsilon over 5. Of course, any smaller number than epsilon over 5 is also the answer. For example, if I take delta equals to epsilon over 6, for example, then I also have the correct answer, because then I will have equals to 5 over 6 epsilon. And then we know that 5 over 6 is always less than 1. Yeah? So it's all obviously less than epsilon. Okay, so the answer will be any number, any positive number, of course, smaller than epsilon over 5. You can take epsilon over 7, epsilon over 13, epsilon over 11, for example. Okay? Any number will do the job. Yeah. Yes.
Greater than 5.
Greater than?
Under 5. Absolute value of x minus 1.
Delta.
Oh.
Here is delta.
Of 5 delta.
5 delta. Okay. Any other question or comment? Okay. Okay, so yeah, any number you can take you can replace 5 here by any bigger number than 5. Okay, for example. Okay, now let us continue. So from part D here, yeah, this is, we have to complete this sentence, the definition of the limit. So here, according to the definition of the limit of a function at a certain point, the meaning of limit x tends to 2 x squared equals to 4 is that here, of course, this for every, the answer will be here for every epsilon. Okay? For every epsilon, and then there exists delta such that, okay, so we have to write the definition of the limit completely. So let us use the whiteboard. For part T, the meaning of limit x tends to 2 of x squared equals to 4 is that means for every epsilon positive, the answer will be for every, there exists or there is delta positive such that, so we should write the implication then. 0 is less than x minus 2 less than delta implies absolute value of x squared minus 4 is less than epsilon. Okay. Okay. So here we have to be careful. If we consider the limit as x tends to 2, then we should keep in mind that x is not equal to 2. Okay. So this is important. X is approaching 2, but x is not 2. And this came from absolute value of x minus 2 is greater than 0. So if absolute value of x minus 2 equals to 0, then x minus 2 equals to 0 or x equals to 2. Okay. So keep in mind that if we consider the definition of the limit, then here we should add the absolute value of x minus 2 is greater than 0. Okay. And of course, this represent the distance from x squared to 4, the distance between x squared and 4 can be made small as we can, smaller as we can. Okay. Okay, can be made arbitrarily small there. Okay, so that's the epsilon delta definition of the limit. Okay. Any question or comment before we continue? Okay, any question or comment? Okay, so if there is no question, so let us continue. So for part E, we need to consider the so-called the limit theorem here. So we have the function f at the at 0. Okay, and also we have another function x squared plus 1. Okay, so here we should apply the limit theorem for the product of the function. Okay, we have two functions, and then if we want to calculate its limit, the product of its limit, then simply calculate its limit and then multiply it. Okay, so okay, I will write the number is e. E here, limit x tends to 0 of f of x equals to 2. Okay, then we want to know what is the limit x tends to 0 of x squared plus 1 multiplied by fx. F of x. Okay, so then just multiply limit x tends to 0 of x squared plus 1. Okay, that's the first term. And then multiplied by the limit x tends to 0 of f of x. And in this case, the first limit, of course, is 1. Okay, the second limit is 2. So we get equals to 2. Okay. Okay. So now let us consider part E. Yeah, actually, the second part is not complete because here we should assume the continuity here. So here the answer actually is not the question is not complete in the sense that we need another information, namely the continuity of the function f itself. Okay, so in this case, but anyway, if assuming that this is the second part of 1e, so assuming that assume that f is or f of x is continuous at x equals to 0, then if we assume that f of x is continuous at x equals to 0, then the limit of x tends to 1 of f at x squared minus 1. Okay, so in this case, yeah, assuming that this is continuous, then I can interchange the role or the order of the limit and the order f of f here. So I will, assuming the continuity, then I will have limit x tends to 1 of x squared minus 1. Okay. Then here equals to f0, and f0 equals to limit x tends to 0 of f of x, and previously we have the value is 2. Okay, any question or comment? Yeah, but yes. Okay, sure. Yeah, the first one is the product. The second one is the composition of the two function, but we need to assume the continuity. Okay. Okay. Any question or comment? Okay, so actually this is, we have to add this to calculate the limit. Otherwise, we cannot evaluate it. The continuity should be assumed in this problem. Yeah. Okay. Any question or comment before we continue? Yes. Where is? Pardon? Why it's x squared minus 1? Because that's the question.
Can I see the?
Okay. This one?
Oh, no, the second one.
Okay, any question or comment before we continue?
Why can we put the limit inside brackets?
Because of the continuity. That's the additional information. It's not, so the question is not complete. The question is incomplete because there is no continuity, but if I assume the continuity, then I can calculate it. Good. The continuity means the limit of the function is so f is continuous and c means the value of the function equal to the value of its limit. So that's the meaning. So in other words, we can write this as follows. So f of c can be written as f of c can be written as the limit f evaluate limit x tends to c of x. So in other words, we can let's say interchange the order of the limit and the order of the evaluation of the value of the function. Okay. Okay. Any question or comment so far? Up to this point, any question? Oh, actually, I missed this bracket. One bracket. Okay, obviously the limit x tends to 1 of x squared minus 1 is 0. Okay. Okay, so let us continue. Now, part F, here we want to check whether the line x equals to 1 is vertical asymptote or of the graph of the function f of x equals to x minus 1 over x squared minus 1 or not. Okay. And yeah, f here, I will write the definition of the function. So here f of x equals to x minus 1 divided by x squared minus 1. Okay. Then if we want to check the vertical asymptote, then we need to check whether the limit x tends to 1 of f of x is infinity or minus infinity, or if we consider the left hand limit or the right hand limit of the function f at 1. Yes. So let us calculate it. Limit x tends to 1 of f of x here. Actually, this the calculation is similar to the first question. Yeah, similar to the 1a. In this case, I will have limit x tends to 1 of x minus 1 divided by the product of x minus 1 and x plus 1. So in this case, since x is approaching 1, the meaning is that x is not equal to 1. So x minus 1 is non-zero. Then I can divide here x minus 1 by x minus 1. Okay. So in this case, I will have limit x tends to 1 of 1 over x plus 1. Okay. And in this case, I will have this one becomes 1 over 1 plus 1, 2 is half. So the limit is half. So in this case, the conclusion is the line x equals to 1 is not a vertical asymptote of. It's not a vertical. Asymptote of y equals to f of x. Okay. Okay, it's not a vertical asymptote. Okay. Any question or comment so far? Yeah. So what is the vertical asymptote of f of x here? Okay, can you find the vertical asymptote of f of x equals to -1? Okay, so let us check whether x equals to -1 is a vertical asymptote of this one. Okay, so here it's sufficient to check either the left hand limit or the right hand limit of x tends to -1 here. Okay, so for example, if I want to check the right hand limit, so limit x tends to -1 plus, the meaning is the right hand limit or the limit from the right of, what is the function? F of x equals to limit x tends to 1 plus of sorry, minus x minus 1 divided by x squared minus 1. So in this case, if x, so the meaning is that is x tends to -1 plus, means x is greater than -1 and x is close or near to -1. For example, you can assume that x is in between -1 and 0, let's say. Okay, x is in between -1 and 0. Okay, and in this case, if x is between -1 and 0, what is the value of what is the sign of x squared -1 there? Okay, so here I assume that x is in between -1 and 0. And what happened with x squared -1 there? Okay, if x is in between -1 and 0, what happened with x squared -1? What is the sign of x squared -1? The sign of x squared -1 is negative. Okay, so x squared -1 is negative. Okay, so x squared, where is the x squared -1? X squared -1 is negative. And what is the sign of x -1? X -1 is also negative as well. So if x -1 is negative and x squared -1 is negative, then the sign of x -1 over x squared -1 is positive. Could you lower your voice because it will be recorded here? Okay, so x -1 divided by x squared -1 is positive, but of course x squared -1 here is approaching 0 there, and x -1 is non-zero. Yeah, so the limit x tends to -1 plus of x -1 is -2, right? It's non-zero, and the limit x tends to -1 plus of x squared -1 is 0. Okay, and the sign is x -1. Okay, so and x -1 over x squared -1 is greater than 0 for let's say x between -1 and 0. So the conclusion is the limit x tends to -1 plus of x -1 divided by x squared -1 is, so what is the answer? The numerator is non-zero, the denominator is 0, and the value of this function for any x close to -1 is positive. So what is the limit then? The limit is? The limit is? Yeah, of course it's positive, but what is the precise? The limit is? Yes, infinity, right? The limit is plus infinity. Okay. So here, the conclusion is the limit x tends to -1 plus of f of x is plus infinity. Therefore, the line, so the line x equals to -1 is a vertical asymptote of y of the graph of the function y equals to fx equals to x -1 divided by x squared minus 1. Okay, any question or comment so far up to this point? Yes?
So when we have to use the x minus one or x plus minus.
Yeah, actually we can replace this by the left hand limit. This is the right hand limit is infinity. The left hand limit should be minus infinity. So I can check the limit x tends to -1. But we do not need to calculate both. Only one of them. If it's infinity or minus infinity, then we can conclude that the line, let's say x equals to -1 is vertical asymptote. Okay. Of course, if you calculate here x -1 divided by x squared minus 1, then we know that x -1 is negative, so the sign is negative, and then the sign of x squared minus 1 is positive, because if x is approaching -1 from the left, then x squared is obviously is greater than 1. So x squared minus 1 is positive. So minus divided by plus, then it's negative, right? So the conclusion will be its limit is minus infinity. Okay? But the final conclusion is the same, namely the line x equals to -1 is vertical asymptote of y equals to f of x. Okay, so the question, the calculation of the limit can be, in this case, the right hand limit or the left hand limit. So one of these two only. Okay. Yes.
5, 8.
8. Yes. Okay. Any question or comment? So far, up to this point, any question? Yes, question? Any question?
Oh, how much?
Okay. Okay, so let us take a look at the picture of this or the graph of this function. Okay, so suppose that let us take a look at the graph. Where is the online? Okay. Oops, I haven't shared. It's okay. So let us suppose that we have the graph of y equals to x -1 divided by x squared minus 1. Okay. Yeah. So you'll see that here x equals to 1 is not the vertical asymptote. The value of the limit is half there. The value of the limit is half. And the vertical asymptote will be x equals to -1. Okay. So you'll see that if I consider the right hand limit, Okay, if I take a look at the graph of the function, the red one, you'll see that if x is approaching -1 from the right, then the value of the function can be made arbitrarily large. On the other hand, if I consider the left-hand limit at -1, then the value of the function is getting really small there. Okay, any questions or comments so far? So actually, you can realize or you can recognize the the infinite limit by take a look at the graph of the function. If the graph of the function is going upward here indefinitely, then the limit is infinity. And if the graph of the function is going downward here, is going downward indefinitely, then its limit is minus infinity. Okay. Okay. Any question or comment so far up to this point? Yes.
For the left hand limit, the result will only for the.
Of course, it's not that the case. If I can switch I can switch the function here. So the left hand limit can be infinity. Just add it, just multiply it by -1. So the left hand limit can be infinity as well. Okay. Any question or comment? Okay. Yeah. Yeah, but to verify the existence of the vertical asymptote, then we only need to calculate one of these two limits. Either left hand limit, right hand limit, or if I consider, for example, if I take the square here, oops, just a moment, it's the same, right? Okay, so the if I consider, let's say, the square here, okay, yeah, it's be careful because if I add this, then square. Okay, for example, here I the left hand limit and the right hand limit is the same, namely it's infinity. Of course, its limit is infinity as well. Okay, so but still we have the vertical limit, the vertical asymptote x equals to -1. Yeah. Okay. Any question or comment before we continue? Okay, so let us continue to the, where is the whiteboard? Okay, so the next one we'll consider. Okay, so now we have the limits at infinity. So there are two kind of limits. The infinite limit and the limit at infinity. Okay. And you see that the difference in part F and G here. Part G here, if the limit extends to infinity of f of x is 2, then what is the unknown here? Then blah 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 asymptote of f is the line. Okay, so what is the answer? What is the answer? Then A. What is the answer? What is the answer? Part G. If then what is the answer of this one? Yeah. What is the answer? Then the answer is the horizontal asymptote of f is the line y equals to 2. The answer is the horizontal asymptote of f is the line y equals to 2. G, if okay, so we have this one is the limits at infinity. F of x equals to 2. Then a horizontal asymptote of the graph of f or of f is the line y equals to 2. Here. Okay. Yeah, so you have to take a look at this, and this is the infinite limit, and the type of asymptote is the horizontal one, and the equation of the line is y equals to 2. So actually, you can take a look at the graph of the function here. If you consider, okay, let's say if I consider the horizontal asymptote here, let's say y equals to 2 minus 1 over x. Okay, so you'll see that the line, if I take a look at the limit as x tends to infinity of this, then I will have y equals to 2 as the horizontal asymptote. If I take limit of x tends to infinity, meaning I move the point on the graph to the right direction indefinitely, then it's approaching the line y equals to 2. Okay? And similarly, if we consider the limit to minus infinity as well. Okay. Any question or comment? Okay, if this is not the case, so I will continue whiteboard and then okay. Okay, so the answer of H is just the definition of continuity. So if f equals to 1 and limit t tends to c of f equals to 1, then f is continuous at c. Okay, so that's the answer. Okay. Okay, so but I let f be continuous on the interval. Okay, so the answer is, okay, I will write the answer in H. Will be f is continuous at x equals to 1. Sorry, x equals to c. X equals to c. The reason is the limit. Oh, sorry, the variable is t, right? Limit t tends to c of ft equals to 1, and 1 is the value of fc. Okay. So the conclusion is f is continuous at t equals to c. Okay. Now let us consider I. And in part I here, suppose that f is continuous on the interval 0, 3, except at x equals to 1. But however, the value of the limit is 3. So we can define we can redefine the value of f at x equals to 1 to be so f1 can be just take, we can redefine so that the function f is continuous. So f1 should be the limit x tends to 1 of f of x, and the value is 3. So we can redefine f1 to be 3. Okay. Okay, so part J here, suppose that f is continuous at on a comma b. If fa is less than 0 and fb is greater than 0, then the question is, okay, can we find the function, the value of the function f so that its value is 0? Okay, and it's a quite intuitive, because if I consider the graph of the function f, let's say, on the interval a comma b, and suppose that what is the sign? Fa is negative, so suppose fa is negative, fb is positive, then if I want to draw a continuous function, namely, I want to draw the graph of the function without removing the pen here, then I should, at least at a certain point, then our graph should intersect the x-axis. The meaning of this is that the value of, let's say, there exists a point C, so that at this point, the value of the function is 0. Okay? So if we have a two, okay, value, the negative one and the positive one there, if the function is continuous, then if I want to connect the negative and the positive sign, then at least at a certain point, then the value of the function is 0, right? Because I want to come across the x-axis. Okay? Then I have to cut it. Okay? And the intersection means the value of the function at a certain point here is 0. Of course, there can be, for example, any possibility that, okay, I have more than one intersection, for example. I have more than one intersection, then it's also fine. Okay. For example, we have 3 intersection there, but at least we have to guarantee that at least the graph of the function intersect the x-axis at least at one point, okay? Because there is a change of sign of the function. The first one negative, or the second one is positive, or similarly, if we consider, let's say, if fa is positive and fb is negative, it's also the case. Then at least a certain point, then we have to cut, or we have to intersect the x-axis. Okay. Okay. I think that that's for the concept review. So let us continue later on in the number 2 or 3, but probably we'll shall take a short break for 5 minutes. Okay.